This video is an introduction to linear programming. First of all, what is a linear programming problem? In a linear programming problem, there are always two components. The first component is called the objective function. And the second component is called the constraints. The objective function is always given by minimizing or maximizing a linear function. When we try to do minimization, we will use C to denote cost. But if we are doing maximization, we usually use P to denote profit. By linear, we mean that every single term must have degree 1 or below. In other words, you won't see x squared or y cubed or x times y, these kind of terms in this objective function. The objective function must be open-ended, and by that, we mean that you won't see, for example, equal to 16 at the end, or greater than or equals to 20 at the end. These are not allowed in the objective function portion. The constraints component usually start with the phrase subject to. Just like if you get a scholarship, you are often subject to certain constraints, such as maintaining a certain GPA. Every constraint should be in terms of an inequality. In the linear programming problems that we encounter at school, I can almost guarantee you that we will only see non-strict inequalities, meaning that you will only see greater than or equal to or less than or equal to everywhere, instead of a strict inequality. This is because if we have strict inequalities, we may not have a maximum or minimum value for the objective function. In most linear programming problems, especially those coming from a word problem, we often have to put in the constraints that all these variables must be non-negative. This is because these variables x and y usually stand for the weight of fertilizer that we're using or the amount of chemical that we put in. Therefore, they just can't be negative. Again, in the constraints component, these inequalities must be linear. In other words, these portions must be polynomials that are of degree 1 or below. Therefore, you won't see x cubed, square root y, or x over y terms, etc. That being said, sometimes we can transform a problem that doesn't look like a linear programming problem into a linear programming problem. Like this. As you can see, there are lots of square terms in this problem. So according to our definition, this is not a linear programming problem. However, if you look closely to this problem, we could replace x squared, y squared, and z squared by capital X, capital Y, and capital Z respectively. And this will transform it back to a linear programming problem. Notice that we have the extra constraints. Capital X, capital Y, and capital Z must be non-negative here. This is because before the transformation, all the variables are square terms, and square terms are always non-negative. So we have to put these constraints back in. Similarly, if the original problem looks like this, with 1 over x, 1 over y, and 1 over z terms, we can also transform it back to a linear programming problem by doing a substitution, like this. Notice that the constraints here have strict inequalities this time. This is because the reciprocals of positive numbers are positive. These strict inequalities could lead to troubles. So this type of problems has to be very carefully set so that we can solve for the maximum value or the minimum value here. So after all these, you may still ask, what are linear programming problems doing? The point of linear programming problems is to do optimization. For example, you want to find suitable sites to set up a couple warehouses in a big city. There are constraints that you need to satisfy. For example, the total footage of warehouses you need so that you have enough space, the maximum transportation time each day from the warehouses to the retail stores, etc., etc. Based on these constraints, you need to minimize the cost of building these warehouses. That is what linear programming is doing. Thank you very much for watching. If you like this video, please subscribe to our channel and we will learn more fun math together. Thank you.